welcome back to the deep dive. If you spend your days, like us, wrestling with large language models, you know the pain, that constant nagging limitation.
The context window.
Exactly. It's the single biggest bottleneck we face for, truly complex tasks.
It really is the wall we keep hitting. You want to feed in a huge data set, maybe a long legal case or an entire code base.
Yeah.
And the compute costs, the memory, they just explode. It becomes completely impractical. That quadratic complexity of self-attention really bites you.
And we absolutely need models that can handle this stuff. Hundreds of thousands, maybe millions of tokens. Think about cross-document analysis, understanding entire code repositories.
Right.
So we've seen lots of architectural tweaks, different attention mechanisms. But today we're looking at something, well, quite different, a really radical approach called Glyph.
Glyph calls it visual context scaling. And it really flips the script on input. Instead of raw text tokens, the idea is to render the long text into compact images, visual glyphs, essentially.
And then feed those to a vision language model, a VLM.
Precisely. A VLM processes these images.
Okay, so the big promise here, and why we're doing this deep dive, is the efficiency gain, right?
That's the core of it. We're talking potentially 3 to 4 times token compression.
3 to 4 times.
Yeah, while keeping accuracy high. So you drastically boost the effective context length.
Without actually making the VLM's own context window physically bigger or needing all that extra memory.
Exactly. So our mission today is to really unpack how this works, the engineering pipeline, the specific stages.
And crucially, those efficiency numbers. How does this actually change the game for running massive context models?
Let's dive in.
Okay, let's ground this. Think about a classic example, something really long, maybe the novel Jane Eyre.
Good one. That's roughly, what, 240,000 text tokens, give or take?
Yeah, around there. So you take your standard, pretty high-end LLM, maybe it has a 128,000 token context window.
Which is already quite large by today's standard.
Right, but it still fails instantly on Jane Eyre. It just can't fit it all. It truncates the input.
Chops off everything after, I don't know, page 100 or something. So if you ask a question that needs info from the end...
Like, who helps Jane out after she leaves Thornfield?
The model has 0 chance. It never even saw that part of the text. Guaranteed failure.
Okay, so enter Glyph. How does it handle the 240,000 tokens?
It renders that entire novel into a visual sequence. But instead of 240K tokens, the VLM sees something more like maybe 80,000 visual tokens.
Wow, okay, so that's the 3x compression right there, just on the input side, before any attention calculation even happens.
Exactly. The magic is in the information density. The VLM isn't reading text tokens, it's processing the glyphs, the visual representation.
So each visual token is like a compact package holding info from several text tokens.
That's a good way to think about it, a compact carrier. If the rendering is done well, you pack more information into each unit the model processes without losing the meaning.
Okay, but let's hit pause for a sec. We've seen context extension hacks before, right? Things like yarn, sparse attention, linear attention. How is this fundamentally different? Time for a neural signal check. Here's why this development actually matters at a technical level.
Yeah, this is a really crucial distinction. Methods like positional encoding tweaks, like yarn, they let you address longer sequences, but they don't make inference any faster.
Right, the compute is still proportional to the sequence length squared, or at least linear for things like sparse attention.
Exactly, and those attention modifications, like sparse or linear attention, they reduce the complexity of the calculation. Sure, ON2 becomes maybe ON log n or ON, but they don't change n itself. They don't change the raw number of input tokens, tau to dollars. The model has to chew through.
Ah, but Glyph does. It tackles the problem from the other end.
Totally orthogonal, yes. It cuts down the sequence length $2 before it even hits the attention layers. It reduces the sheer volume of input.
And that token reduction immediately means less memory needed, right? Especially for the KV cache.
Precisely. That KV cache saving scales linearly with the sequence length reduction. And as you know, the KV cache is often the real killer for deploying long context models. That's where the memory pressure really builds up.
So this isn't just some simple text-to-image script. It sounds like quite an involved process.
Oh, absolutely. It's a multi-stage engineering pipeline. 3 tightly coupled stages, actually, to get the VLM properly aligned for understanding these long rendered documents.
Here's stage 1.
Stage 1 is continual pre-training. The goal here is basically cross-modal transfer. You need to teach the VLM, which might be good at understanding natural images, how to reason about these dense text-based images over long contexts.
So training it on rendered text.
Massive amounts of it. And crucially, they used a really diverse data strategy. They didn't just render plain white pages. They used different visual styles.
Like what?
Things like document style, web style for how pages look online, code style with syntax highlighting.
Oh, interesting.
Even dark mode and something they called artistic pixel. The idea is to make the model robust so it doesn't get thrown off if the font changes or the background color is different.
Makes sense. And what kind of tasks did they train it on?
A few families. There were standard OCR tasks, just reconstructing the original text from the rendered image to make sure it can actually read.
Okay.
Then interleaved language modeling. This is clever. It forces the model to switch back and forth between processing text snippets and image snippets within the same sequence. Builds flexibility.
Right.
And finally, generation tasks. Things like filling in missing parts of a rendered page, forcing it to understand the surrounding visual context.
Okay. That covers pre-training. What's stage 2?
Stage 2 is where it gets really optimized.
Yeah.
LLM-driven rendering search. This is key because, as it turns out, the VLM's performance is super sensitive to how the text is rendered.
Sensitive how? Like font size, spacing?
Exactly. Font size, DPI, dots per inch, line spacing, page layout. If you compress too much, making the font tiny or cramming lines together.
The VLM just can't read it accurately anymore.
Precisely. Performance falls off a cliff. So you need to find the sweet spot, the best rendering parameters that give you maximum compression without sacrificing accuracy.
And they used an LLM to find this sweet spot. You mean an AI optimizing the graphic design for another AI?
That's exactly it. They used an LLM-driven genetic search algorithm.
Wow.
The LLM looks at how the VLM performs on a validation set for different rendering settings, checking both accuracy and the compression ratio achieved. Then it suggests new mutations to the rendering parameters. Try a slightly smaller font, maybe increase the DPI, change the page margins.
That's incredibly meta. Using an LLM as a design consultant to figure out the best way to present information visually to another model.
It is. And they found the optimal configuration was surprisingly specific, like down to the exact font and size.
What did they land on?
The paper mentions an optimal setup using 9-point Verdana font at 72 DPI on a specific page size, 595 by 842 pixels. That specific combo gave the best trade-off.
Fascinating.
Yeah.
Okay, so they find the perfect rendering recipe. What happens in stage 3?
Stage 3 is post-training optimization. Now that you have the best way to render the text, you fine-tune the model specifically on data rendered that way.
How?
It starts with supervised fine-tuning, SFT. They use curated examples, but crucially, they format the desired outputs using a thinking style format.
Thinking style. You mean like showing its work?
Kind of, including explicit reasoning steps, often marked with tags like think within the generated answer. This encourages the VLM not just to spit out an answer, but to actually perform step-by-step reasoning based on the compressed visual input it's seeing.
So it forces deeper processing of the visual context.
Exactly. And after SFT, they use reinforcement learning, RL, to further refine the model's policy. They use something called Group Relative Policy Optimization, or GRPO.
Okay.
The key here is the reward signal. They used an external LLM as a judge to compare the VLM's output against the ground truth, rewarding accuracy.
Makes sense. Standard RLHF approach.
Pretty much, but with a twist. They also included an auxiliary OCR alignment task during RL.
Why? Didn't the pre-training handle OCR?
It did, but VLMs can still struggle with recovering very fine-grained text details perfectly, especially after focusing on higher-level reasoning. So during RL, they added a reward based on character-level accuracy using Levenstein distance to penalize text errors.
Ah, so it keeps the model honest about the low-level details, even while optimizing for high-level answers. Like, don't forget to actually read the text accurately.
Exactly. It addresses that challenge of maintaining fidelity to the source text within this compressed visual domain.
Okay, that whole pipeline, pre-training, LLM search, SFT with thinking traces, RL with OCR checks sounds incredibly thorough. So after all that, the payoff. Let's talk results. The efficiency gains.
This is where it gets really exciting for anyone thinking about deployment. On standard long context benchmarks, things like long bench, MRCR, they consistently achieve that 3 to 4 times average compression ratio.
3 to 4x. Okay.
And on some tasks, or in specific experiments, they pushed it even further, hitting around 5x, even showing potential for maybe 8x compression in some settings, so there's likely still room to grow here.
That's impressive compression. But what about speed? Does processing images slow things down compared to text?
That's the surprising part. Compared to the original text backbone model running the equivalent uncompressed sequence length, say 128,000 tokens,
Yeah.
the pre-filling latency, that initial crunch to process the entire input context, was sped up by up to 4.8 times using Glyph.
Whoa, almost 5x faster prefill at 128K.
Yes. Think about what that means for inference cost and responsiveness. Suddenly, processing those massive documents becomes much, much cheaper and faster.
That's a genuine game changer for practical applications. What about generating the response, the decoding part?
Also significant gains. Decoding throughput saw speedups of up to 4.4 times at that 128K effective length. Even the fine-tuning stage, the SFT training, was about twice as fast because it was processing shorter sequences.
Okay, let's spell out the scaling advantage here. This input compression seems key.
It absolutely is. If you take a standard text model and you manage to double its context window, say from 32K to 64K tokens.
You've gained 32K tokens worth of context.
Right. But with Glyph, at say 3x compression, if you expand its nominal visual token window from 32K to 64K,
You've effectively added capacity for roughly 3 times that amount of original text, like 96,000 text tokens worth.
exactly. That 32K expansion in the visual domain translates to a much larger gain in terms of the original text context it can handle. And we see this in the results. Glyph's accuracy holds up much better as the input documents get longer, compared to text models struggling with those longer sequences. Its performance degrades much more gracefully.
And did they see any other benefits? Like, does training on rendered text help with real images?
Interestingly, yes. They tested it on multimodal benchmarks involving real documents, like mmlong benchdoc. And the Glyph model, despite being trained primarily on rendered text, actually outperformed the original VLM backbone it was based on.
So the robustness they built in during rendering search actually generalized.
It seems so. That diverse visual training seems to have benefits beyond just handling rendered text. It made the model better at understanding complex visual document layouts in general.
Okay, this sounds incredibly promising. But no technique is perfect. Let's dig into the nuances, the trade-offs. You mentioned the performance curve.
Right. The source material is clear. It's nonlinear. You can't just keep cranking up the compression indefinitely.
That's why the LLM search was needed, right, to find the balance.
Exactly. Push the compression ratio too high, make the text too small, too dense, and the VLM simply can't resolve the details anymore. Accuracy plummets. Finding the optimal tataga is crucial.
And what about the DPI finding? You mentioned resolution.
Yeah, this was fascinating. They found that even after training with the optimal rendering settings, like 72 DPI, if they simply increased the rendering resolution at inference time, say, rendered the input at a higher DPI, the model's accuracy often went up significantly.
So the model could actually handle more detail than it was trained on.
It suggests exactly that. The underlying VLM seems capable of resolving finer visual details, implying the performance ceiling for this visual approach might be even higher than what they achieved with the current rendering pipeline. There's untapped potential in the visual processing itself.
Okay, but what about the limitations they did hit? What are the current weaknesses?
Well, one is definitely the sensitivity to rendering parameters we discussed. While the search found an optimum for their test sets, ensuring that robustness holds up across any random font, document style, or weird spacing found in the wild, that's still an open challenge. Real-world documents are messy.
True. Any other major hurdles?
The other big one is OCR fidelity, especially on certain types of text. The paper specifically calls out problems with sparse alphanumeric sequences.
Like what? Product codes, IDs?
Exactly. Things like long random UMIDs, which pop up in benchmarks like Ruler. The VLM struggled badly with these. It wasn't that the characters were blurry, it was more that the model would misorder them or substitute characters.
Why?
The hypothesis is distributional sparsity. Those kinds of long, random, non-semantic strings are just very rare in the typical text the models are pre-trained on. So the VLM hasn't learned robust patterns for perfectly recognizing and ordering them, especially when they're densely packed visually. This definitely puts an upper limit on performance for tasks requiring perfect fidelity on such strings.
Got it. So future directions. Where does this research go next?
The paper points towards a couple of key areas. One is training adaptive rendering models,
Meaning,
meaning the model itself learns to choose the best way to render a piece of text based on the content or the task. Maybe code gets rendered differently than prose, for example.
dynamic rendering optimization.
Potentially, yes. And the other big direction is just continuing to improve the visual encoder itself, making it inherently better at fine-grained text recognition within images.
Makes sense. Improve the VLM's eyesight for text.
Fundamentally, they believe by refining this visual representation, pushing the alignment and robustness, they can scale context much further. It's a breakthrough because it changes the input itself, not just the model architecture.
Right. It shifts the bottleneck. This move from pure text sequences to these compressed visual glyphs.
Yeah.
It's clearly unlocking major efficiency gains in memory and speed. 1 million tokens seems genuinely feasible now through this kind of compression.
It really does put 1M tokens on the table in a practical way.
So that leaves us with the final provocative thought for you, our listener, to chew on. If Glyph, or techniques like it, make 1 million tokens achievable, what's next? What are the fundamental technical roadblocks we'll hit trying to scale context to, say, 10 million tokens?
And how will visual text compression itself need to evolve? Can we get 10x, 20x compression reliably? What new challenges arise when the rendered input itself is millions of visual tokens long?
Lots to think about there. A fascinating direction for scaling LLMs. As always, to keep up with the latest deep dives into AI and ML, make sure you visit our webpage, neuralintal.org.
And check us out on YouTube as well. Thanks for joining us.